Next. And so, okay, at least you are fine. So, our next presenter discussing discussing the paper consistent estimations of finite mixtures and application to later improve panel structures by Raphael Langevin. Okay, he introduced to me that yesterday twice, and I'm messing up in it. So yeah, go ahead.
Great, thank you. So, for those who've known me for a while, this is sort of coming back to finite mixture models. Thank you, Matt, for assigning me this paper. For those of you who don't know, now you know that I've been thinking about this forever. So it's great to be back, and it's been a real treat to kind of read and think and plot through the equations of Raphael's paper, because there's a lot in that paper. And I've learned a lot. I've been thinking about it a lot. I Zoomed with him a couple of days ago because I'm like, okay, you gotta help me out here because I'm stuck. So all of this is to suggest that it's a paper worth reading. It's a paper worth thinking about. It's a paper with some really sort of interesting advances in this literature on finite mixture models. That's where I'll start. And thank you, Raphael, again for sharing your slides. So a lot of the equations I did not have to retype because that's a pain, as you all know. Right? So okay. So what this paper does is kind of 4 pieces, perhaps, if you want to think about it like that. It starts with a sort of a theorem and a whole bunch of stuff that I will cast doubt about later. So we'll hold that kind of a bit, which is to say that kind of the traditional way people have done these mixture models, the estimation of the parameters, is sort of provides inconsistent estimates. Right? And I think the way I'll kind of reframe it is that we know that those methods have problems because these likelihood functions are really complicated with multiple maxima, and people have been aware of it, but kind of there aren't any alternatives, so people keep doing the same thing over and over again, and you kind of hope you get the right answer. So the second contribution of this paper, which is to suggest a different type of estimator, this max component likelihood, actually is a way to get around some of those problems, right? And so now there's a bit of a horse race, in my view, about kind of which works better when. And I think Raphael has some very sort of convincing evidence that precisely when the maximum likelihood estimator doesn't work so well, this max component likelihood estimator will work very well. That's sort of the third part in a simulation exercise or in a series of simulation exercises. And then Raphael kind of models individual healthcare expenditures from administrative data over time, and I'll show you his results, and it's sort of kind of very, very insightful again. So I'm going to kind of do what as presenter discussants have done so far, which is to sort of present it as Raphael might. So these are really his slides. So usually you think about kind of the mixture density as something like this. This is kind of a very simple form, but that's in some sense the canonical form, a set of probabilities that are in this context constant, with densities f sub g, the densities with parameters, right, parameterized by thetas. Typically people think of the same f, so it's a mixture of normals, it's a mixture of exponentials, it's a mixture of somethings. But of course, in principle, you can have different densities as well. And I'll come back to that idea when I get to the empirical example. And then the probability sum to 1 is the standard sort of close the model assumption. And that's, I think, key here. So it's been around forever. It's been around since the 1950s when they didn't have computers, but people were still thinking about these kinds of statistics. And I think Heckman and Singer, brought it into economics, I guess. It's safe to say that they were the first to do it. I've done some stuff in health. It's all over. It's in game theory. So there's experimental stuff in economics where people use these things, and you think about it. You tell a story about types of people, types of agents. You saw the structural paper this morning. Essentially, there were lots of sort of finite mixture models hiding around in structural language. And then of course in the new computer science and machine learning literature, there's a lot of stuff, right? So it's pattern recognition, machine learning literature is full of it. Okay, so what are the issues, right? So for people familiar with these models, you immediately know kind of what the issues are. So this is really kind of a primer for everyone else. Is that first you have to assume that you know the number of components for any of the asymptotic theory to go through. Yes, and is it 2 classes? Is it just good health, bad health? Are there 5 types of health? Should we? So all of those questions that come up in empirical analysis are important questions here. The analyst is required to make a stand about the number of components, and then of course, you try, you do some post hoc testing to say, well, is it 2, is it 3, is it 5, is it whatever, right? I have always leaned on, statement that Heckman made, which is to say, there's only 2 types of people, or 3 types of people, or 4 types of people. That's it, right? So I'm like, if he said it, I'm good. Okay, it's never more than 4. Right, so I think he sort of pretty much said it like that too, but obviously I'm not him. Okay, so that's important though, and that's going to play a role in identification, right? So if you don't know, if you're not sure, you might sort of misclassify models. You might get the wrong answers because you've picked the wrong number of components. And then here's a very classic picture. This is from Raphael's paper, right? That if you take 2 normal distributions, that's what you see on the top panel over here, and these 2 normal distributions are pretty close to each other in terms of their means, then the mixed density looks like that. And if I hadn't shown you the top, you wouldn't be able to distinguish the top from the bottom, right? It looks like it just could be another normally distributed random variable. You wouldn't know that it's a mixture of the 2. That's important, because that means you're going to have a really hard time identifying the parameters of the mixture, because even your eyes tell you that they're they're not distinguishable. Okay, so now that's important. That's where the EM algorithm or the maximum likelihood algorithms really struggle when separation is small. So you hope that separation is high enough. You run your model. When you get really wacky results, you change your data, your tempo, you try whatever you can do, and then eventually you get estimates. Yes, and I think Raphael makes a compelling case in some of the simulations that that's not okay, right? There might be a signal there in those weird estimates you're getting when the pi's essentially go to 0 or 1, that in fact you have a poorly separated distribution. Picture on the right hand side, now the world looks much more like the textbook finite mixture. Great. Okay, so here's your maximum likelihood. I just set it up. That's the density, mixed density, you write the likelihood, it's pretty simple. Okay, and then traditionally what people have done is estimate it via EM. So the idea is you fix the pi's, you estimate the theta parameters, that's your M step, then you go back with an expectation argument, and you get a new set of pi hats, and then you keep doing this until you converge, right? Others, me, and I would say this data implementation, for example, does a whole bunch of these EM steps that hopefully takes you closer to the global maximum, no guarantee, right? And then when you're close enough, you switch to a classic Newton-Raphson, then you can get estimates of pi with standard errors, et cetera, which we like to see. So does it really matter? They both kind of are essentially maximum likelihood techniques and kind of have the same kinds of issues. So standard set of assumptions, and Raphael will argue in the paper that in fact you get sort of a first order derivative condition for the pi's that are always bounded away from 0. So that's a problem. Okay, and I'm going to come back later and suggest why I think that's kind of a little bit perhaps misleading, right? So, but I don't think it's necessary to kind of argue that this paper has lots of very, very good stuff to keep reading on. I got hung up here, but I got hung up here because I was like, wait a second, I can't get past this. I've been doing this too long. Raphael's saying I've done it wrong. Not just me, everybody's done it wrong. Okay, I couldn't get past that, so I called him. Anyway, so we talked through it. We agree, I think now we're in a better place, sort of ish. So we'll go past that later. All right. Let me suggest what sort of an alternative an alternative that has been hinted at in a paper this morning, right? So this is a finite mixture problem. So you think I've got different densities. I've got to sort of classify my observations into one or the other or the third density. You can turn this around and make it a classification problem, right? From the new sort of machine learning literature where classification problems have become sort of much more commonplace with lots of sophisticated methods applied into trying to classify observations. So that's exactly the frame in which sort of Raphael's contribution lies, is to say, let's turn this into a classification problem. Let's not think about the likelihood in the way that we've done so far. Let's not call it pi times f, but instead, let's think about it as z times f, right? Where z is the classifier. So if I knew which density you belong to, which class you belong to, then I've got a very simple problem. Does that mean, yes, that's if I knew that. So the hard question is, how can I classify? Okay, but this is where sort of the entire machinery of classification comes to your rescue, that there are ways to classify observations into groups, right? It kind of was used earlier today, and so think of k-means as a very simple-minded way of doing that, but that's the basic principle along which this new estimator, that's what it hinges on. So the idea is change the way you think about your likelihood that requires you to classify each observation into one or the other density. Then you've got a pretty simple problem to solve. That's not hard to imagine. And the hard problem is to get the assignment of z correct, right? So you're going to assign z equals 0 or 1 based on some criterion function that you're going to set up, right? And Raphael will argue that there are at least 2 or 3 that make a lot of sense. Under some conditions, there's one that's really much more powerful than the rest, but maybe you don't like all of the assumptions that you have to make to get there, so you might try one of the other 2. But the idea is basically, if you have a distance metric, then broadly put, then that distance metric h, you maximize that, and that gives you this assignment to 0 or 1, right? So that's the key here. Once you're done with that, you've got, if you get the correct, so there's an oracle kind of property that's lurking in the background, as with many of these things. If you get z right, it's kind of not hard to imagine you get the thetas right. Right? That part's sort of relatively easy to think about. Okay, so again, I think I sort of jumped ahead, right? So these are Raphael's words. So the question really is, how can we guarantee that z is the truth asymptotically without sort of putting other restrictions on group membership? Yes, because there are other ways to solve that problem, which are all restrictions. Okay, Raphael's answer to this question is essentially a classification problem. So you need covariates here. Without covariates, how are you going to classify? So the argument is there's something out there, there's information out there that allows you to classify. Okay. Once you do that, so again, because I jumped ahead, so we can do this based on a joint density. We can do this on a Euclidean distance, kind of a very traditional Euclidean distance measure. We can use the Mahalanobis distance, which is really powerful if you assume multivariate normality of these covariates that you're going to use to do the classification. Maybe they are, maybe they aren't, maybe it's a good approximation, but regardless, you've got a set of ways in which you can calculate these z's, right? And I think that's the key here. Okay, so what Raphael does is show, and this is hard work, this is complicated work to say, A, there is a set of z's that gets you to the right z, the truth, asymptotically. And then once you have that, you get the correct thetas, right? Conditional on knowing the correct z's, okay? So the first part of that theorem is, I think, kind of the hard work and the hard part, and really a big contribution. The second part is not so hard to imagine, because now we have kind of a pretty traditional density function to think about, right? The Fs. Okay. Am I doing on time? Good. Right. So I'll come back to this because in order to show that the classifier is consistent, you need to say something about the number of covariates relative to the number of observations. Yes. In this notation, if you're kind of following along, then there's an n and there's a t because kind of he's thinking about it in both in a t and n dimension. But you can ignore the t, just think cross section, and you have n, the sample size, and you have p, the number of covariates. Yes, and the asymptotic proofs that are required here require p relative to the sample size to go to infinity. Right. So that's it for the typical kind of empirical researcher. I'm going, wait, right? But that's actually not so different. That classification literature is exactly that, right? And you'll see that in the simulation and in the empirical application, the practical thing is that p can be pretty small. You know, the theorem requires that p goes to infinity, but in fact, small finite p gives you very good answers. Yeah, so just keep that in the back of your mind. I think it is not at all inconsistent with a lot of the machine learning literature that essentially says this is what you need. You've got to be able to slice and dice your data until there's kind of nothing left. That's the intuitive way to think about it, but you can get away with small p. Okay. Then I will show you the results of his simulation in a slide. And you'll see that in fact, this estimator under a whole bunch of conditions does better than the traditional sort of EM-based maximum likelihood estimator, right? I will make a point here that I will come back to, that this is a simulation that's done in this sort of panel data space. So there's an n dimension, there's a t dimension. These classes in the DGP are evolving over time. So it's a pretty complicated mixture problem. And maybe that's exactly what you want. I'm going to show you some stuff that's very, very simple so that I can abstract away from some of these dimensions. But to the extent that this is the DGP, the simulation results show that maximizing this max component likelihood outperforms EM under certain conditions, right? If the mixture has no really small size component. So, you know, if you have components of 0.95 and 0.05, even EM is problematic, right? Because you have very few observations in one class. That problem gets exacerbated in a sense when you have to predict the Z, right? So you have to predict the Z, you have to say this, and you're going to have a hard time with those really small probability groups to predict that Z. And you need the misclassification rate to be zero, near zero, at the true parameter values. Yes, so this is not that hard. We're not talking about the estimates. We're saying that if you knew the true Z's, you would never misclassify an observation. I think that is kind of not a complicated assumption to absorb. What do we get? So big numbers are bad, right? That's kind of very simply, these are weighted root mean square errors. And you can see that the orange is the EM, the blue is this new estimator, right? The max component. And you can see that in most of these cases, here's an exception, right? Where in fact, this max component likelihood estimator does better than the traditional EM estimator, okay? Are these differences sort of meaningful for an applied person to sort of worry about? I don't know, that's a question I have for Rafael, yes, but from an econometric perspective, sort of in some sense, you've shown that that estimator, the newly derived estimator, does better than the old estimator. Okay, the empirical application, I will just say a couple of things about, and then I'll kind of talk about some thoughts I had. The empirical application again, is in a panel data context. So there's a T dimension and an N dimension. And here, Raphael is using the mixture model to focus on classification, right? To think about groups and how these groups transition potentially over time, yes? This is not a question of focus on the thetas. It's not about treatment effects given the group, which is kind of how I've thought about mixtures a lot. This is about the groups themselves, yes? So having a panel means you can think about dynamics of how these groups change over time. The model here is a mixture of two-part models. I'm going to come back to that because the two-part model itself is a mixture, right, of things. So that's hard, right? So the fact that Raphael is doing this kind of makes it a hard mixture problem to solve on a good day, just because identification is very hard, right? There's mixing going on inside the two-part, and then there's mixing going on outside the two-part. Come back to that. I think that's a tough one. Okay, there's a set of covariates. I'm not going to spend much time. I think Raphael does a very good job of sort of convincing the reader that, in fact, it's not just I took my sample, I compared two numbers, look, one's better than the other, because he's doing tenfold cross-validation and showing that every time you do this, you get better answers if you use the classifier rather than EM. Okay, and that's sort of over here, right? How much better? I don't know, right? So these are kind of the estimates or kind of relative mean squared errors. Sometimes, this is the case where the EM algorithm seems to kind of provide incredibly wide sets of estimates. You're all over the map, as I would say. But then other times they're not as good, but how much worse? An open question, I think, right? Because it's hard to sort of know what this relative root mean squared error, which is kind of a weighted average of things, actually means, right? What's the interpretation? How good is that? Okay. Here's the groups. So there's 1, 2, 3, 4, 5 groups here, right? Health states, health groups that Raphael identifies. And here's how they transition. So given how much time I have, I'm just going to kind of leave it there. I think you should take a look at this stuff in this empirical example in Raphael's paper if you're interested, because I think it's fascinating. The empirical results on their own are quite interesting, although clearly Raphael's paper is about is more than that. Okay, so just very quickly, I'm going to go back. I'm going to tell you why I think that sort of this argument that the MLE or is inconsistent is sort of not quite right. Here's sort of the likelihood function, okay? And this is from Raphael's paper. This is the equation I sort of pulled in. And you get this F term over here. And this F is positive. The sum of the F, the weighted sum of the F's is positive. So that's going to be greater than 0. That's the argument, right? But I think this leaves out something super important, which is that the pi's have to sum to 1. So you don't actually have G pi's, you have G minus 1 pi's, right? I think if you're talking, it's not just a weighted sum of densities. It's a weighted sum of densities that is mutually exclusive and exhaustive. And I think exhaustive here is important. So if you do that, you get pi G, just right, without generality, pi G is 1 minus all the other pi's. And if you take the derivatives again, then you get a difference in the two densities every time you do this. And the difference in the two densities can be equal to 0. So that's the problem you want to solve, right? So I think I've been thinking about this. I've been worrying about it. I've been like, eventually I talked to Raphael about it. Because I'm like, what am I doing wrong? So then I went back to, I don't trust my own calculus anymore. So I'm going to go to the computer, okay? And I'm going to do what Raphael says I should think about. So here's an example from his paper. This is not the picture that he showed, but this is pretty close to the picture that he showed. The two densities, both unit normal, and the mixed density with probabilities 0.5. So, again, if you looked at the red, you wouldn't really know that it was a mixture of two normals. I'm going to assume I know it's 2. So I'm going to write down the likelihood function. I'm going to maximize it. I'm so lazy that I use theta's FMM without checking for global maxima. Yeah, so I'm just going to let it start with the default, not recommended for any real exercise, but I'm going to start with the default and I'm just going to run it through. And here's what I find. That's my estimates of pi. As the sample size increases, it's exactly what I expect, right? And then here's my two means, right? So to me, that looks like a computer proof of consistency. If you bring those two densities very close to each other, that's kind of Raphael's picture. Now, this looks even more difficult to distinguish from the two distributions. And now you see some of the issues that Raphael is sort of hinting at. Here's what you get vis-a-vis pi. So if you cut off your densities on the sides, right? I think I have 1,000 draws, so plenty of data. Then it looks like, well, it is getting better. But in fact, there's substantial weights in the tail. So pi goes to 0, pi goes to 1. That causes then everything else to fall apart, right? And you see that falling apart here. So now, I don't want to call this inconsistent because I haven't gone to infinity, but even with 40,000 observations, I am not centered at the truth. I'm not centered there, I'm not centered here. Okay, so I am out of time. I did the exponential, it's all good there. I am out of time, but I will just say one other thing about the empirical application. Panel data is really complicated here if you're serious about the fixed effects, the individual level fixed effects, because individual fixed effects could just sweep out your mixture, right? If you think about it naively. So now I have to think about it really sophisticatedly to say, I've swept out the individual's fixed effect, and yet they are different types. So it's not impossible, but it's hard, right? So I think it's well worth thinking about that. And then the two part is also a mixture. So that's complicated. So there's lots of complication in the application. So I think kind of developing that further, just sort of trying to tease it apart to say how much of it is due to the panel stuff, how much of it is due to the two part stuff would be great. Thank you.
You will now the response from Raphael. 10 minutes for it.
Great, thank you. Okay, thank you very much, Partha, for the discussion talk today and 2 days ago. First thing I want to say that let's agree to disagree. Let's agree to disagree. There's no problem in that. So I'm going to try to convince the audience that indeed there is a consistency problem. It's not like identification issue. I don't focus much on identification because like you can assume point identification if you have like mixture of normals, exponential. So this is something that's been dealt with in the last like 40 years. And when you know the true number of groups, you don't have like, this problem of over specification in the number of groups. So here it's really about estimation. Can we converge to the true parameter value? And so I'm going to respond to like 5 of the comments created to Partha. And first I'm going to start with the exactability of pi, because when Partha told me that 2 days ago, I was like, yeah, that's relevant concern. So I'm gonna try it. I'm gonna try it because I tried it before, didn't get something really interesting. No one really does this. No one really does the exactability of pi's. They use instead the posterior mean of the posterior probabilities. The posterior probabilities being the probabilities of being assigned to each component for each observation. Average over that, and this gets an estimate of the mixing weights, instead of trying to solve this problem here. So the above problem where you maximize over pi the log likelihood function subject to this unit constraint, but also to a non-negativity constraint where all the pi's need to be positive. And it could be also strictly positive, but let's say here is only positive. It might be equal to 0. Econ 101, you need to derive the Counter condition in this case. It's a lot easier, think about it, when you just remove the sum, when you look at only a single observation. When you look at only a single observation, this is just like a linear programming easy problem where the corner solution is obvious. IG is equal to 1 for the GF component that maximizes the value of density across all components. Does everyone see that? If someone does not see that, we could have coffee together during the break. So summing over the observation, does this change the nature of the solution here? That's what I thought was thinking about it during my flight, and I could not give a really convincing answer. But here, the fact is that we account for the unit constraint and the non-negativity constraint, and there is a corner solution for a single observation. So yes, I think we need to think again more clearly about this issue. But at the end of the day, what's the choice? So Partha presented you like some simulation results. I've got other results in the paper that he didn't present. And we have this estimation procedure that I propose that does well in simulation, that does well also in theory, at least according to me, compared to another procedure that has been there for decades, but often yield poor results. So it's up to you. If we look at the simulation, so first question is, you just said it, like you use the FMM SATA command for the simulation. I'm not sure what exactly it does, but here, if we look here exactly at the same problem, I have exactly the same simulation in the paper, and if we look here at the pi's, when the true mean value, so it's a mixture of two components, two normal densities with unit variance, and mean equal, the true means are there. If you look at the pi's here, you can see that the corner solution, or almost corner solution, is quite clear here, and you get to the true pi's as the distance between two mean values increase. Okay? So we'll have to talk about it later on, but it's strange. It's strange what you get as a result. So I was wondering if what you plotted is the likelihood of pi's given the true theta. So because if it's this, like everything's fine, like the pi is going to be the density is going to be maximized at the true value. But what is interesting is when you plot the likelihood as a function of both the pi's and the theta, and the thetas are two mean values and two variances. And there it's going to be a lot messier than the nice graph that Partha just showed. And also the case with big G is equal to 2, so two components and all mixing weights equal to each other, 1 over big G, is an easy case. If we look at, like, for instance, let's say a G is equal to 3, and unbalanced mixing weights, like in this table below, where you have like the true mixing weights here, so 1/6, 1/3, and a half, and number of observation 1,500,000. You can see that in the mixing weights here, the columns that are flipped, sorry for that. The mixing weights also are very poorly estimated when the true mean values are quite close to each other, and we get to the same result that the pi's get correctly estimated as you increase the distance. But I agree that there are still theoretical stuff to do here, but at the end of the day, if you pick one or the other for practical implementation, I think that apart from this theoretical issue, I think that what I'm proposing still do a better job. So asymptotic with respect to P. So the number of covariates, as Arthur said, I increase it to infinity, but a relatively small number of covariates does pretty good in practice. And I don't need for consistency, and by consistency, and that's the important part here, by consistency in classification, what I refer to when I'm talking about consistency in classification is the classification error rate going to 0 as the sample size increases. Not that all observations are correctly classified. To be consistent, a sufficient condition is that the proportion of misclassified observation goes to 0. So some observation might still be misclassified, but you will still converge to the true value, both in terms of group membership, not of group membership all, but in terms of the theta. So if your focus is on group membership for all observation, you might get some wrong, but still you will get the thetas for each component correctly and asymptotically converging to the true value. And in this case, you don't need to have a lot of covariates. P over N or NT might be relatively small. In fact, there are no rate at which P has to increase to get consistent estimate, and that's one of the main results of the paper. And also, like using covariates or multivariate outcome, if you don't have any covariates, you can use just like different outcomes and assume that group membership is similar across outcomes. And if you have enough outcomes, this will give you enough information to drive down classification error. So that's pretty much what Keening does with no covariates. And if you can have both, that's also great. So computer scientists and statisticians do it quite often to use covariates and let the number of covariates increase. I think we should try to leverage that in the future work, whether it's to relax group membership assumption as similar to the work we've seen this morning. Okay, complexity of the application. I'm going to go quite fast on this. So the two part, and let's agree to disagree once again, it's not a real mixture because you know where you belong. Like the first part is the binary part, and you know that like the outcome is one, you've got a strictly positive value, and 0, you have a 0 value in your healthcare expenditure. Let's talk about healthcare expenditure. So in this first part, if you take all strictly positive healthcare expenditure, make it equal to 1, you got your outcome. You use this separately to model your logic or your product model. The second part, you only use the strictly positive expenditure and you model that separately. This relies on an independence assumption between each part, but this assumption is much weaker when you use a finite mixture of 2 parts compared to standard 2 part, because if there is correlation within group, you account for that with the mixture. So basically here is just to show that it's not that complicated. Yeah, of course, I've been working on it in the last 3 years, so it means it's not that complicated, but there is a case here for simplifying the 2-part model under the impedance assumption that should maybe relieve some people. And yes, transition allowed. You didn't really talk about it, so I'm gonna leave it out to the room for question. Thank you.
So question, open to question. I want to hear, yeah.
Yeah, can I ask, I was very confused when you were saying, no one ever gets the MLE for the pies. What do you mean? And so what does everyone do?
So what most of people do is using this definition here. So the average of the posterior probabilities. So you could do that, or you could try to model the group membership using a multinomial logic model. Stuff more complicated, but a lot of people actually do that. So compute for each observation and each component, compute the probability of being in this group, and you average over the observation for each group, and you get an estimate of the mixing weights.
I think I've always done it the way you say, no one ever does it.
Then no one, when I say that the exact MLE is that it's not well defined in a sense that there's no analytical solution apart from the one that I'm advocating, that the exact MLE will give a corner solution. But I'll be happy to derive it and to try to make it work if it works.
But I guess another point is another way you could go is just do a Bayesian analysis, right? Where you could set up a Gibbs sampler, and in one of the steps you draw the membership. Right. So I've done it that way too.
Yeah,
That seems to work pretty well.
It relies on the likelihood being, if it's, so if there is an inconsistency in the likelihood, or sample size increase, the posterior estimates in the Bayesian framework is likely the mean of your posterior density might not be exactly located on the true value. So yes, the overall shape of the posterior density might look fine, but the posterior mean of the density might not converge to the true value of the likelihood is not consistent.
Why don't we talk more later?
Well, there, you have some drinks and coffee too.
Yeah, of course.
Now, next question.
This is just a clarification, and this is obviously a very complicated model, but one of the main thing about your suggestion about the classification and the latent mixture, conceptually they're different things because your classification is based on X's, so it's a fancy nonlinear model, whereas the latent mixture is based on Y completely, right? And you cannot do your procedure with Y because that will be just conditional density estimation, right? So I wonder if you can talk a little bit about that.
So the main assumption in my procedure to converge to the true value is that the grouping pattern in the outcome is similar to the grouping pattern in the covariates, especially for the second moment, the variance covariance matrix. If it's not the same, you could just use the covariates if there is some pattern that's relevant, but of course it has to be the same at some point, because if you're modeling the outcome on a grouping that's totally different from everything else, yes, you get nonsensical results. That's the main assumption, and especially on the variance covariance matrix, the mean can be different, or the grouping pattern on the mean of the covariates can be anything. But if you have p covariates, you estimate those p-square matrix. It has to follow the same grouping pattern as the outcome to be able to pin down the true thetas. Otherwise, you get into this problem of component density that might be too close to each other. In the component density in terms of the outcomes, yes, indeed. That's why you need more information in order to shrink the possible states to recover the group membership.
But your groupings are all deterministic, right? Because it's based on X's and you're just doing k-means or any kind of grouping. And so this is establishing heterogeneity in a deterministic fashion across groups of X's, which is very different from what the latent mixture kind of does, in my opinion.
I'm not sure if I understood correctly your question, that if we assume that there's a true group membership out there in the real world, and that you define a mixture density based on that, or any kind of latent class generating data process, it's practically speaking, is gonna lead you to the same thing.
Right, but you're not doing latent class, are you?
That's the same logic behind. That's exactly the same logic behind. So when you generate a mixture, what do? You specify the number of groups. You specify for each observation or you specify your mixing weights, and after you say, okay, half my observation are gonna be generated by this density, and the other half, if the mixing weights are equal, are gonna be generated by this other density. And after you get the mixture density, and you get the same
But the
problem.
density is of the density of the Y, the outcome variable.
Yeah, here's why, what I'm saying is that in order to get the true group membership asymptotically, if you don't have additional information, there is an impossibility theorem there, especially when the density of the Y's are too close to each other.
Good, any more questions? We have time for a couple, or? He's offering coffee or a drink for later, so probably that wasn't a good idea. Well, if there are no more questions, we are done with session 3, and we have a break, a coffee break until 4 p.m. Yes, 4 p.m. We're back for the panel. Thank you so much. A round of applause again. Thank you.